Attend AutoCon 2 in Denver, November 20th through 22nd, 2024. You'll hear presentations about network automation from hands-on engineers who built automation systems for their company and have the scars to prove it. Conference pricing is not high, but this is a boutique event with limited tickets. Go to networkautomation.forum/AutoCon2 to register today. Welcome to Heavy Networking, the flagship podcast from the Packet Pushers Podcast Network. If you've ever had to explain to someone that spanning tree doesn't cause loops, but in fact it prevents them, you've found your tribe. Some quick housekeeping for you. There are new podcasts in the Packet Pushers Podcast Network. The first is called Technically Leadership with host Laura Santamaria. And the second is Total Network Operations with host Scott Raban. I will say more about those at the bottom of the show, but just wanted to let you know that they exist. Type Technically Leadership or Total Network Operations into your podcast client and subscribe. On today's episode of Heavy Networking, Rob Sherwood joins us to discuss the impact high-performance computing and artificial intelligence computing are having on data center network design. And it's not just a story about leaf-spine architecture. That's actually the boring part. There's also power and cooling issues and massive bandwidth requirements and changes in how we think about network interface cards. Should they be smart? Should they be dumb? Or both? To speak on these opinions is, again, Rob Sherwood. Rob, welcome back to Heavy Networking. It's been a while, man. I don't know how long it's been since you've been on Heavy Networking. Quite some time. So before we get into this HPC AI networking discussion, would you remind people who you are and then share with us what you've been working on lately?
Always happy to be here. Thanks so much for having me. Who I am, I don't know. I've been doing networking for more than 30 years now. I've done the math. I've done everything from research in research labs to operating some of the largest networks in the world to shipping products and startups. I'm currently running my own startup now, NetDebug, which actually has nothing to do with what we're talking about today, but all fun and games.
Okay. Well, again, Rob, welcome back. And as you say, you've been around a long time. You've been involved with lots of startups. You've done a lot of things. You've been involved with shiny new technology and brought it to life, new ideas, and so on. And if you're out there listening, you want to dig back in the deep in the Packet Pushers archives, look for shows that we did with Big Switch Networks back in the day. And Rob, you might have been on some shows we did about OpenFlow way back in the day too. Yeah.
Yep. And I've even done a couple kind of wax philosophic shows as well, which I think this falls more into that kind. But
yeah, because this does feel like it's going to be more of a philosophical show. We were chatting the other day, and you cited these 4 big topics you wanted to discuss around HPC and AI and how it's impacting data center network design. And you said collective communications, power and cooling, bandwidth, and then lots of stuff around what the NIC looks like today and re-architecting it and so on. So we're going to have an unstructured conversation today, Rob, just kicking around on those 4 topics that you highlighted. So first of all, as related to data center network design, collective communications. What do you mean by that and what's going on here?
Well, and let me even step a little further back and talk about the problem. So my mental model of folks running an average network right now is they probably have some storage traffic going on. They probably have some RPC. They might have some web requests or something like that. And all of that works on, what the fancy term is statistical multicasting, which is, basically saying, as long as it doesn't happen all at once, then, as long as you're okay with the long tail of, the 1 in a million, web gets slowed down, but everybody else is kind of okay on average, then you have a pretty good network and life is good and you don't get fired, right? I think that's kind of a typical network for most people. But most people have also heard about this AI thing. And it turns out that the way AI communication, specifically AI training, works is completely orthogonal and in some ways potentially even damaging to that network. And so
and just so we're very clear, Rob, we're not talking about artificial intelligence itself as the traffic that is generated as AI computing workloads are sitting on top of the network.
Absolutely. And I should clarify, there's really 2 types of AI compute workloads. One is called training, which is, I have a bunch of data and I want to make a model that, this is how you would figure out, how to make something like ChatGPT. And the other is inference, which is you already have the model and you just want to run it and ask it questions. And the making the model is, and I don't mean to talk big, but it's basically the most compute intensive thing that we as humans have tried to do.
This is the
Yeah,
thing that we're hearing about that's consuming all the power, and people that are concerned about the environment and so on are going, do we really need all these LLMs and so on because of all the power that's being consumed, et cetera?
Absolutely. And the good news is once you've got the model, and that should be like an infrequent operation, like running the model, the inference part is much easier. But turns out the big arm race is in the making the model right now. And that was the thing I really wanted to dig into because it has just like massive impacts on how you run a network and design critically.
So in that context then of making a model, what is the issue with collective communications and how does that differ from, what's on a typical network or how a typical network operates?
So a typical network uses what everybody would know and love called unicast, which is you've got one source, you've got one destination, and on top of that, you have lots and lots of sources and destinations, and that's where you get kind of the statistical multiplexing. Collective communications is everybody does the same thing at once in lockstep. So a typical collective communication might be a reduce operation. So imagine you've got thousands of nodes, each with one integer, and you want to logically add up all of those integers and have the result end up on one machine. Usually they have a special machine called the root node, but it ends up being just a kind of an arbitrary machine. And so if you think about like what the packet of that, like the packet processing of that looks like is, it's really easy for 1,000 machines to send a single packet to one machine all at once. But in most contexts, that looks like a denial of service attack. Right. And so,
but that's actually how this model training is supposed to function. All of these packets of these computations have to be sent to one place simultaneously or nearly simultaneously.
It gets more complicated than that, but this is our building block.
Okay.
And what happens? So there's two things that make it more complicated. One is you have deep pipelining. So the result of that one thing leads into the next round of doing this. So you actually have, millions of these operations in a row where the ith one has to finish before you can move on to the ith plus one. So it's like, so what that means is that like if at step 1,000 somebody drops a packet, then everything has to stop, slow down, retransmit that packet or whatever you're going to do with that. Or even if it's not drop the packet, maybe it's just there's a lot of queuing and it gets delayed. Like that jumps the computation of the entire end-to-end thing. And if that happens with some frequency, then what could have been, only an hour's worth of computation is now a day's worth or 2 weeks worth or something. And so you end up
that
in
bad?
this. It can be.
Wow.
So, I mean, if you run the numbers for, you see these latency numbers off of switches where it's like, 10 nanoseconds for a packet to go port to port without buffering.
Yeah.
Right. But like with buffering, you can get up to the milliseconds. So that's like 100x or 100,000x. And then if you include packet loss in there, then you certainly could potentially can get worse depending on how aggressive your packet retimers are and things like that. And so it really can't, because it's both lockstep and bursty doesn't begin to cover it. It is the most bursty thing that you could create on a network where everybody in lockstep is sending all the packets all at once to one place. It's an incredibly difficult networking problem to solve.
Now, again, to one place, that's so as I've been hearing about these AI clusters and the way they do their thing, I was imagining the chunks of data distributed across multiple GPUs and sent for computation and the answer sent to one place. Is the answer that big?
Well, so I'm doing so. So there is a set of libraries called the Message Passing Interface, MPI, and they're the core for a lot of high performance computation. And AI is like one specific application built in high performance compute. The operation I'm talking about is called reduce, and that's actually not what AI uses. AI uses a related operation called all reduce, which is that much more complicated. So in all reduce, not only are you sending all the traffic to you actually send all the traffic to all the nodes. So imagine you have, each node has say you've got 1,000 nodes, each one has 1,000 numbers, and you're sending the first of those numbers to the first person, and the second of those numbers to the second person, and so on and so forth. So you're actually doing this reduce in parallel across all the machines, and that's one clock tick.
Yes. Thus the quandary Ethernet finds itself in, not very well suited for such a thing.
Yes. And we'll put that on the stack because look, Ethernet has lots of tricks up its sleeve to try to fix things like this. But immediately you start to understand why people historically have looked at things like InfiniBand that will do hop by hop queuing and things like that, or you have rate control built into the process. But if you think about, okay, that sounds crazy. How do I run this on top of my existing network with bursty communications and WebGets and RPC calls and all sorts of stuff like that? And the answer is you don't. Almost every shop that I know, eventually including Google, which Google was the last holdout for this, has built a physically separate AI training network. So you would have machines basically with multiple interfaces, some for like the production normal fabric, where you have kind of the statistical multicasting, best effort network, and then some interfaces for the back-end training network. And your listeners probably remember the days of physically isolated storage networks. It's roughly the same idea. But just the traffic is so completely different that you actually need something like this.
Yep, and then all the pains of converged networks were around this. How do you prioritize the stuff that needs a certain performance profile and have it share gracefully with everything else? It complicated the network configurations for sure.
And so, and this is why I got passionate about wanting to talk to you intrinsically about, to your listeners about this, is like that is such a completely different shift from how you run normal networks that if folks are sitting at home thinking, oh, yeah, I'm just going to do AI training on top of my existing network, you're not going to get good performance out of it.
So the assumption is you should be building a dedicated network. If you plan to build an AI model, you should also be planning to build a standalone network for it.
That's, in my mind, the current best practice. In full disclosure, I think that's still being debated, but in my mind, the answer is pretty clear.
Well, would it matter how big the model is you're training?
Yes. So, and maybe that's a good point. So there's two dimensions of size for a model. There is how many different inputs you want to take into it. So how many tokens, if you're familiar with that terminology. And then there's how many training examples you have. And so if you're the number of tokens you want to take as input exceed what you can put on a single GPU, then you have to start dividing it across multiple GPUs. And companies like NVIDIA will sell exceedingly beefy dedicated AI training platforms that'll have upwards of 8 GPUs in them. And so then you're still dividing that model across the 8 GPUs, but if it fits in that, you're only going across a local systems bus rather than like a full-on network. But if you look at some of the big models like Llama out of Meta, or ChatGPT's model, or Google's model and whatnot, those end up being divided not just across 8 GPUs, but tens of thousands.
Right.
And
because of all the tokens that they're working with, and tokens is essentially a chunk of data. I guess I'm thinking in the LLM context, it's like a word or a chunk a chunk of letters or a phrase.
It roughly approximates a word. I think my understanding, and this is where my understanding gets a bit knowledge, like as you get to bigger words, you actually subdivide words.
Right. Yep.
But roughly a word is the way to think about it. So that's one dimension of how this gets big. But the other dimension is the number of training samples. And so if you imagine you have, a million pictures of, food, and then a classifier which is like hot dog, not hot dog, is kind of the classical example.
Yes, I was waiting for that reference.
Yes, it's a great show. Depending on how many you have of those, you may actually want to not run all of them on one machine. You also want to subdivide that, and then what you do across this multi-dimension size of your model by number of training samples is those get divided across GPUs. And then you do this iterative algorithm called backpropagation, where you run all the samples through all the models and you see how good it does. And at first it does really badly, but then backpropagation basically upvotes the pieces of the model that got you closer to the right answer, and then downvotes the pieces of the model that got you away from the right answer.
Mm-hmm.
But it uses gradient descent, so you just do a little tweak to the upvote and downvote of these models, and then you run it all again, and then you run it all again, and then you run it hundreds of millions of times. And it's that backpropagation that ultimately uses the all reduce under the covers.
A quick interruption to tell you about AutoCon 2, the third in the AutoCon conference series about network automation. Only, don't think of AutoCon as a typical conference. Instead, AutoCon is a gathering of the networking industry to work towards a standardized approach to network automation. And this is a hard problem. Equipment vendors have a vested interest in selling you their automation tools, but let me guess, you're a multi-vendor shop. There are so many open source tools you could bring into your automation stack that it can be overwhelming. And if you want to integrate with products like ServiceNow, that is an added complexity. If you've tried moving from simple Python scripts to a robust automation system the business can rely on, you know what I'm getting at. And this is why the Network Automation Forum exists, why the AutoCon conference series exists, and why you should attend AutoCon 2 in real time in Denver, November 20th through 22nd, 2024. Hear the talks, interact with the speakers, talk to other attendees in the hallway track, meet the people making automation tools, talk to vendor experts who live and breathe this stuff. You're going to leave with solid ideas about how to approach network automation for your company, ideas that will impact the business that you support in a very positive way. Register at networkautomation.forum/AutoCon2. And I don't mean to sound dramatic, but don't wait, because this event is almost certainly going to sell out, and the venue only holds so many humans. There really is a ticket cap. Again, that's networkautomation.forum/AutoCon2, and I hope to see you in Denver. And now, back to the podcast.
So if I've got a separate network for this, for the training, what does my host look like? Do I end up with a host stuffed full of NICs that have interfaces facing a bunch of different networks in this modern architecture?
If you build it yourself, yes. And in fact, what gets interesting is that some of the more advanced models of these, you start actually needing a NIC per graphics card. And so then you could, if you did this naively, you could actually end up with the PCI bus being the bottleneck.
Yeah.
And then you end up with NICs on graphics cards. And so, and that's for the AI training network, but then you also have separate, normal NICs for your production network.
Well, hang on. NIC on graphics card to skip the PCI bus problem, you mean?
Exactly.
Okay, tell us about that.
Well, and it's an evolution, and let me just qualify. A lot of this depends on what scale you're talking, right? If you're looking to compete with, Facebook, Microsoft, and Google, then you end up with, NICs on graphics cards and, a sea of these things and potentially custom chips that you start producing and, networks in the size of, tens of thousands of nodes. There's a bunch of other interesting data points for folks who are less ambitious, which is to say the rest of the world. And so you'll have to steer me for which end you think is more interesting for your listeners.
Yeah, I mean, I think it's good to touch on both because we want to get a sense of, sort of the big guys pushing the state of the art versus what folks might be intending to try to do on their own. So I think it's helpful to talk a little bit about both.
Yeah.
So yeah, let's start with the big ones then. It sounds like custom silicon building NICs right onto GPUs, and again, that's to avoid any PCI bus penalty.
But any sort of contention, like the entire point of a bus is to have this point to multi-point network, if you want to think of it, inside your servers. And if you actually get to a scale point where you want a NIC per GPU, you don't even need a bus. You just directly connect them. And, if you're going to have that there, then it's like, okay, well, do I need, so maybe another point, do you guys know what RDMA is?
Yep.
Mm-hmm.
So,
but if you want to just give us the overview, because it's helpful.
Yeah. So super critical operation for modern PCs is DMA, direct memory access, where normally you don't want to, for every word that byte that you move around in your machine, if you're going to move a million bytes from this part of memory to this other part of memory, you don't want to have a CPU operation per byte, right? And so there are some nice primitives that allow you to say, memory, don't interrupt the CPU, just copy from here to there and get back to me when you're done. And that's DMA, local DMA is how to think about it. And then RDMA is the network equivalent of that, where there's a special packet format that if you set up your NIC the right way and if you set up your memory areas the right way, you can actually do fast copies from one machine to another without interrupting the CPU. All of these operations, DMA or RDMA of some form is critical, because at the rate that packets are coming in and out, you don't actually, for most training, you don't want your CPU involved at all. You really want it to be mostly on the GPU. And so what ends up happening as data comes in off the NIC is, by RDMA, it will write the packet memory directly into the GPU RAM.
So RDMA is getting me CPU bypass from one endpoint to another endpoint.
Correct. And then if that is your baseline, then it's like, oh, why do I even have the NIC on the PCI bus at all? Why don't I just hook it up directly to the GPU?
Yeah. Why bother? Why risk that the PCI buses, which in this scenario, if I've got multiple GPUs on board, the PCI bus could indeed be a bottleneck. You could have contention.
Absolutely.
And so, yeah, this makes all this. Now that's, I mean, it's, I don't know if it's infinitely scalable, but I mean, as many GPUs you could stuff into that box, in theory, you can put a NIC on board and get all the data in and out of them.
And, I think for most people, building their own box is probably not ideal, although that won't stop a lot of people because it's a lot of fun. There are companies that put out basically pre-built server boxes, NVIDIA's A100 and more recently H100, and they're coming up with more of these things, right? But so you get a box that I don't know the total power dissipated. It's obscene, but you get things where it's like there are 8 GPUs internally connected via NVIDIA's like NVLink magic, which is, think of that as its own little bus, and then externally connected with 8 400 gig NICs. So 8 by 400 gig gets you up to 3.2 terabit per box.
Wow. Yeah. And then presumably you've got multiple of these boxes you're connecting to a network.
Yeah, if you have enough money and power. And legitimately, like, power becomes a big issue.
Yeah, we're going to get into that, but I just want to, so we were talking about sort of the far end of the example spectrum. What about if I'm a large enterprise? I decided I have some use cases for training, for building my own training model. What kind of infrastructure am I looking at? Is that where I'm getting into buying an NVIDIA H100 or whatever?
So what I would suggest is that there's kind of a decision tree, which is, how much training and how often are you going to do it? And cloud, like using the cloud, is probably the right thing for, I would say, at least 50% of folks. Right?
Essentially rent the infrastructure to train your model.
Absolutely. It's like, because you have to look at not just the hardware costs, but the expertise costs. I mean, there really are like new skill sets here that, like, if you've been doing networking for 20 years, but you haven't been doing HPC networking, this is just completely different.
And is that because we're assuming InfiniBand here, or just because of the, demands of the workload?
The demands of the workload. And I will actually throw out that my money is still on Ethernet long term versus InfiniBand, but that's kind of a contentious point that we can push towards the end. So, and you could chalk that up to, one of the hats that I had was when I was working at Intel, I was trying to make that case professionally. So that might just be historical professional bias.
So the larger context here was, what does the host look like in one of these setups? It does sound like we end up with multiple networks. We're going to have the HPC/AI compute network that looks odd, different from what you were describing, with direct inputs into the host. direct NICs interfaces into the host, and then other interfaces that talk to things like a management network and a backup network, and I don't know what else, that kind of thing.
So critically, you don't want to under provision that network as well, because most of the training data doesn't live on the AI HPC network. It lives on the standard, regular network. So you still have, a lot of data that comes in for storage. Like, so in our hot dogs examples, as you're loading 1 million high resolution images, that's non-trivial amount of bandwidth. And so what's complex about this from a systems design problem is you have a pretty complex and deep pipeline that could be rate limited by any one of these steps.
Okay, so you're saying I've got the compute to do the model training. I've got the network to connect up the various nodes that need to be connected. And then I've also got some kind of storage network that has the data that my model is going to be trained on, and they all have to integrate and synchronize.
Correct. And, when I say storage network, I really mean storage network workloads. I have not seen, for example, anybody using fiber channel or FCOE or whatnot in these types of designs. They're using standard, iSCSI or what have you. I'm probably dating myself. I'm a storage network person, but it's like I think of it as like you have your standard production network, and then you have your AI HPC network, and usually people are doing best effort, storage over the standard network is the pattern I've seen.
So NFS, some kind of an object store, something
potentially,
like that.
Yeah, exactly.
I think when you said iSCSI, you did date yourself a bit. Yeah.
Okay.
I don't know how much of that's in production anymore these days.
Not a storage guy. Not a storage guy.
Yeah. This is the problem. Like, if you've been doing this stuff long enough, it's like you walk away for a field for 5 or 10 years, and you come back, and all the 3-letter acronyms are different. You're like, God damn it.
The 3-letter acronyms are different, even though the architecture is like, oh, this is still awfully familiar. Yeah. So, okay. So you said, I'm not going to build my own box. You said half the people are probably going to want to do this in the cloud anyway. But if I am standing up my own data center for these purposes, is there a box I'm buying from Dell, whoever, that is kind of built for this? They're tailored to this market?
So everybody and their brother has a kind of a dedicated server for AI training. And generally what it looks like is a ridiculous amount of power for the power supply, because it's well beyond the normal power volumes. It has 4 or 8 graphics cards in it, and it has 4 or 8 NICs in it that either that end up either going directly to the graphics cards, or you have the appropriate size PCI buses so that's less of an issue. And depending on how people want to, depending on different models of this, and then you'll have some number of network cards not for the AI training network as well.
Okay.
But
and just physically, I assume we're not talking like the sort of pizza box size. These are bigger multi-rack.
Oh, yeah. I mean, these are not multi-rack, but
not multi-rack, but multi-RU.
Like 8U is the typical size that I've seen here.
Wow. Okay.
Chunky.
Chunky, and I don't want to quote the power dissipation numbers, but like it works out that if you have a historical data center where you've allocated 8 kilowatts or 10 kilowatts per rack, you can generally only put like 1 or 2 of these in it per rack, and you end up like if you're retrofitting an existing data center, it looks very funny because it's like you have like a 1 8U appliance per rack.
What sort of NICs am I going to find in these boxes? Are they SmartNICs, dumb NICs, a combo?
Different things for different roles. Again, channeling previous employers, even quote the dumb NICs are actually quite smart. Like if you think of all the stuff, like that they need to do RDMA, and RDMA is a pretty advanced operation. Yeah.
And so to qualify, I mean, what I'm getting at with the SmartNIC is, I can offload some pretty fantastic stuff these days. I mean, off to full NFVs, depending on what the card actually is. If it's an IPU, DPU, depending on what processing functionality is on them. So that's more where I was getting at.
Yeah, no, I know. And there is actually a bunch of standard offload features that you would get out of a traditional dumb NIC don't apply here. So like TCP offloads, it's a critical performance enhancement in traditional networks, and it does nothing in an RDMA network. So RDMA is a critical capability. So there's actually some NICs and some SmartNICs support actually in-network collective operations. So there was this work that we did with P4 where instead of sending all the numbers to a host for the host to add them up, imagine the switch could do that. And you could reduce the number of packets going to the host. And so there are instances of people doing things like that. And in the best case, you can actually cut your bandwidth in half. And you might say, okay, well, a factor of 2, that's not that big of a win. But when your factor of 2, we should talk about bandwidth as well. But when the factors, when the base is as high as what we're talking about here, a factor of 2 is huge.
So I'll end up with different kinds of NICs depending on what network they're facing and what they're being asked to do. As you said, RDMA is a key component. I may end up with a true SmartNIC/DPU sort for certain applications. And is it kind of predictable, or is it going to depend heavily on what I'm building?
I will tell you that this space is being hotly contended over, and different sites that I have seen, different sites that I've seen have done wildly different things here. And I think this is the state of the art of networking is exactly deciding how smart we want that NIC to be. And noting that the overall power budget of the system is a big source of both cost and complexity. If you just magically say, well, I'm going to buy the beefiest, smartest NIC that I can for this, you may blow out the rest of your power design.
Wow.
Just because, the per GPU, per NIC part of the equation is pretty substantial. You have a lot of those.
Well, okay. So do we need to talk about bandwidth then? Because it sounds like this is predicated on, 400, 800 gig.
Yes. Well, and not just so there's a couple interesting aspects of bandwidth. So in like a traditional leaf spine, you would have some level of oversubscription, like the ratio of ports that go from the leaf to the spine. And an AI training network, you cannot have oversubscription. You must be, full box bisectional bandwidth. 1-to-1 oversubscription, if you want to think of it that way.
Yeah.
And it is entirely possible for a training run to be network limited. And so that's why you start to get, in addition to 8 NICs per box, you end up with these are either 400 or 800 gig NICs looking at, 3.2T or, 6.8T coming out of the box. And you get to interesting things where it's so a thing that I got pulled into in a past life is, okay, if you start metering out all the numbers and whatnot, we all kind of hand wave and say, oh yeah, bandwidth just doubles every couple of years, right? But the power efficiency of that does not correspondingly double. It does improve, but it's improving linearly.
Mm-hmm.
And so what that means is the fraction of power that the network is using as a fraction of the whole is actually going up substantially.
Coherent optics?
So there's a bunch of ways to start to deal with it. But so critically, no AI network that I know uses DAC cables down to the leaves. So it's optical from the shouldn't say that. For power, if you are power conscious, you don't use that. When you actually buy these things, you get SFPs and you get to do what you want. And if you're not doing too many of them, then you can probably still use a DAC. But because power ends up being a significant cost, and in a lot of ways a limiting factor on scale, I'm seeing designs where it's actually optical down to the servers. And actually there's thoughts about doing optical local to the device, because the power lost with the electrical signaling at the bandwidth rates that we're talking about here.
Now, for the bandwidth requirements, do we need this much bandwidth because we're talking about super large frames, or it's just such a high volume of traffic that has to get out?
It's such a high volume of traffic that has to get out, and it has to get out to everyone all the time.
Mm-hmm.
And the cost of queuing and the cost of packet loss is so high for the overall computation.
Meaning the length of time I would extend my training run if I had to do a lot of queuing or retransmission.
Exactly.
Are these pipes full for a very brief burst, or are they full a lot?
Well, so if you do the rest of the system design the right way, they should be full a lot. And so what ends up happening is the GPU does a bunch of computation, and then you do a bunch of sharing with this all-reduce algorithm. And so that would create it kind of bursty, but it would mean that the CPU is waiting on the network, and then the network's waiting on the CPU, and then you only get half utilization. So what they end up doing is they actually do pipelining at that level. So it's you do a computation, you ship the result over the network to everyone, from everyone to do this all reduce operation while you start working on the next computation. And so I don't know if you guys have seen that movie.
This system.
Yeah.
Well, you're going to chase the bottleneck forever. There's always going to be another bottleneck. It's going to be CPU, it's going to be GPU, it's going to be a bus, it's going to be network, it's going to be
your storage load.
Yeah, stuff off the storage. Exactly. So forever, it's just going to be not somewhere in there. There's going to be a bottleneck. There just is, and you'll chase that one down, fix it, and then the cycle will continue. You'll go right back around again. So can we talk about? Well, are we done talking about bandwidth? We know it's massive.
Go on.
Sorry, go ahead. Yeah, I've got a question about ASICs. So if we're assuming Ethernet and are there specialized ASICs I should be thinking about, or am I going sort of off the shelf?
So let me give you a variety of answers for this, because you've asked one of my favorite questions. Traditional HPC is very Mellanox and InfiniBand focused. Mm-hmm. And there have been some scaling challenges with that. And certainly it is more expensive than traditional Ethernet. There are companies that are doing traditional Ethernet with some smart scheduling. But, so I probably shouldn't share with you research ideas that I've had, but not yet had a chance to chase down. But this is a very active space right now. Actually, so what I can share.
I know that, Broadcom has talked about their some signaling they can do inside their ASICs. In I think the Jericho 3 AI.
Yeah,
they can do some scheduling. Yeah.
So a bunch of ASICs will support a feature they call dynamic load balancing. So normally, when a packet comes into, say, a top of rack from a server, and gets it hits ECMP logic to decide which of the spines it's going to go up to, right? Mm-hmm. If by bad luck you get picked to go to a spine that interface is already bottlenecked, it's already queuing packets, then you either get queued or your packet can get dropped, right? Mm-hmm. Mm-hmm. So what dynamic load balancing will say is, I know all of these links are roughly equivalent, and I know it might cause some reordering, but it'll cause a bounded reordering in most cases. So if my basically it computes two possible uplinks to use, it has a primary that it checks first, and if that has queuing, then it picks a secondary. Mm-hmm. And with that dynamic load balancing feature, you actually can get pretty good spread of traffic across your network, and it saves you from these little micro bursts and micro hiccups that can happen in your network and these types of timescales. Mm-hmm. So I know people are doing stuff like that.
I've also heard about things like, so I don't know if tokens or credits is the right word, but there's a signaling mechanism where an ASIC can say, I have data to send, are you ready to receive? And that the target node can say, I'm ready to receive, and I will give you this credit to let you send, essentially.
And that's the core technology that goes into InfiniBand.
Okay, but they're trying to migrate it essentially to Ethernet then.
Pieces of it, yeah. Okay. And then what I'll tell you is good but also problematic about that technology is all of those are actually hop by hop. And if you have a bigger multi-hop network, just because you got through the credit system of the first network doesn't mean that you can actually get end to end, which is what matters.
Okay. That makes sense.
Another super interesting space, stop me if this is too far, but Google has been pioneering and other people are following optical circuit switches for these networks. So are you guys at all familiar with what optical circuit switches are?
I think of it more as a layer one technology where you're assigning a light wave end to end. Is it that, or am I off?
Yeah, probably the easiest ones to understand are the MEMS mirrors based ones. So imagine you've got a switch with hundreds of ports, and rather than doing packet switching, and it doesn't actually really understand packets, you program it to say everything that comes out of port number 1, I want you to send out port 37 all the time. And everything that comes out of port 25, I send out this one, and you can create like a mapping to and from these things. And so what happens is
we've talked to a startup that's launching with, I think, exactly what you just described. Yeah. Okay.
And so in an AI training sense, what you can do is say, well, maybe I have a network which is the size of the number of ports I have on a switch. And I can actually decide I can send things either across multiple hops. So I send a server, if I want to send to server D and I don't have a direct connection from me to server D based on how the optical circuits are set up, that I can find some intermediary server that I can send to that is transitively connected. You can do things like that. And there's a bunch of games you can play like that. The optical technology is really exciting to me because the power cost of doing that is much cheaper.
Yeah.
So that's another area, but this is we're verging on cutting edge research.
You have no contention at that point either.
Exactly.
You end up with a direct path between the two endpoints that you connect across the optical matrix, if you will. They're it's like a patch panel.
Exactly.
To plug it in one to another. Yeah.
And some of them are literally patch panels. Actually, one of my favorite technologies is a set of robot arms that actually moves plugs across patch panels.
So we're just rebuilding the old telephony network then.
But with robots, so it's better.
Yes.
Yeah.
Actually, what I love about that one is it's not obvious, but it actually requires advanced math, so you don't actually tie knots in your cables. Like, if you just kind of like naively move them around, you'd eventually get knots in the cables.
Yes, wow. So another bandwidth related question, Rob. 1.6 terabit is coming up in, let's say, the next 2 to 3 years, something like that. That's the time horizon. Does that change, or how does that change the game for our conversation so far?
I think it has a couple implications. So one, anything above 400 gigabit, you really start to get bitten by the power cost of the network. So this is the point I was going to make earlier, but I got distracted. Historically, if you look at a large data center, the fraction of power that was consumed by compute versus the network was like 5%. And so the value of a green switch, or friends of mine have posted smarter routing algorithms that will save you power and whatnot. Like, the value of that in a world where your network is 5% of your total data center power cost is almost irrelevant. But as you start to cross 200 gig, 400 gig into 800 into 1.6T, the network becomes a bigger and bigger cost of that, to the point where, I want to say off the top of my head, at 800 gig, it becomes 50% of the total power spend is your network.
Wow.
Well, okay, so let me just pause for a second here. Now, I said coherent optics earlier, and you kind of didn't react to that, but this is one of the arguments we've heard made about coherent optics, is that it helps you with that power problem, to kind of keep the power requirements the same for 800 gig that you had for 400 roughly.
And it helps. But, so basically, because this is at the end of the day, and this is a statement that I think is easy to say and subtle to appreciate, we're building supercomputers. These are tightly coupled end-to-end systems. And coherent optics is an incredibly useful technology that solves one piece of this larger pie puzzle. And, if you say, okay, we'll have coherent optics on the NICs on the servers, and then we'll have optical circuit switches across the network, and we'll do something smart inside the bus for the inside the servers themselves. Then you start hacking away at all the things that start causing a lot of power consumption.
Okay. And so back to 1.6 terabit per second, then you're saying, I mean, I was asking you from a context of speed and you immediately went to the power problem. So is the power problem going to be that severe?
That's my understanding. Now, admittedly, everybody with a PhD who could spell AI is trying to figure out how to solve this. If folks are interested in more about this, Google for Microsoft Powerwall. That's the term the Microsoft folks, the first that I seem to call this out, called this, where it's like, if you track power consumption by the bandwidth of the NICs, you get to this wall of power that needs to be solved. Admittedly, to your original question, once you get to 1.6T, you will be able to train bigger models, smarter models, and whatnot, with less scale out, and so that will unlock the next level of AI in a way that honestly I'm not qualified to speak to. But as far as I understand, the only thing that actually needs power or bandwidth at that level is AI. Like that is, I mean, I would guess most of the people listening to this are currently running 10 gig networks, and maybe some of them are running 50 or 100 or something like that, and they're running with the fudge I'm talking about.
Okay, Rob, anything else to bring up regards to bandwidth before we get back to the because we do need to dive into the power and cooling in a little more detail.
Yeah, I think that's it. I mean, at the end of the day, the AI training workloads are the only ones that I know that need this much bandwidth, but also it really pushes baked in. There's a baked in assumption to most of networking that best effort is okay. And you can actually get packet loss in lots of different parts of your network. Even like after a packet's been delivered from a source to the destination, it can be dropped in the NIC if there's not enough buffering, or it can be dropped in the kernel if there's not enough buffering there and whatnot. And as you start to hit bandwidth speeds at this level, like some of the end host properties become a problem, because even full framed packets at 1.6T or 3.2T or 6.8T coming in, like it really starts to add up. And so there are issues that can happen there as well.
All right, so let's move to power and cooling, Rob. You've mentioned how significant the network is becoming at 400 and 800 gig of the overall data center power budget. You haven't talked much about cooling at all. I mean, I've been reading up on that lately because sustainable cooling at data centers is a thing. The amount of water that is required to pump through a data center to remove the heat is significant, to the point of affecting the local townspeople, if you will, because of just how much water the data center is consuming. So talk to us about it from your perspective, power and cooling.
I think there's a lot of interesting technologies on the horizon coming here, and it's really hard. It's difficult to talk about any one of these pieces in isolation because they all impact the other ones. The collective communication forces more bandwidth, which causes new NIC architectures, which all of with this dissipates more power, which has more and then things that people aren't really thinking about, but like as the amount of power for networking goes up, there's an obvious cost to networking, right? To power. The limiting size on how big of a supercomputing cluster you can build can often be how much power you can get from the local telephone company, the local power company. And they are reluctant to make, in their mind, which is a 50 or 100-year investment based off of the tech fad of the day. So if it's like, well, pretty please, pull up a new nuclear reactor, I'll pay you. Like even if you have the money, they may not be willing to take it because, there's no guarantee that you'll be in business over the lifetime that they depreciate that kind of asset.
To the point of it's become pretty common in reading about new data center builds that the biggest challenge to stand up that new data center facility is in fact power. There isn't enough. You can't generate enough megawatts or gigawatts and pull it in. it's not there. It's not available to be done. Well, we'll build more. You can't. There's nothing to build. There's nothing to do. You've exhausted the resources with which you could do that. And so there's a limited number of sites that can even house this. I know the state of Virginia in the United States is fighting exactly this. There's more data centers and more data centers and more data centers that are being requested to be built, and the power budgets can't be found. It's not from a lack of will or desire. It's just there isn't the facilities to actually erect a power structure, a power generation structure to feed the data center. So what do you do? And this seems to be a big dilemma for data center operators right now.
Well, and it is a correlated problem. So I live in California. Lots of clean energy. Yay! I like green energy. If you move to a more sustainable, what we'll call inverter-based power network. And so what inverters, so you imagine like a solar panel that produces DC current, you have to change that into alternating current. And the device that does that's an inverter. It actually creates this interesting problem of inertia in the power network, which is, if most of your power is being generated by big spinning things like a hydroelectric dam or in a nuclear reactor, if all of a sudden somebody turns up, another gigawatt because the AI training job started, those devices, the big spinning thing, the device will slow down a little bit, but not so much that it causes a massive brownout across people. And hopefully that's enough time for the power company to power up some more things to kind of offset that. You're
talking about on-demand power, that the concern there, and
yes.
A turbine being impacted by this other device coming online.
But that problem is exacerbated as more and more of your power is basically generated via inverters. So you end up with this complex distributed systems problem of, if you imagine there's 100 million homes, each with 10 kilowatts of solar on their roofs. What is the signal that can get to those devices to say, Ethan and Drew's, massive AI training job just started, better, connect to the network again. And how quickly does that happen?
To kind of buffer the rest of the grid from the demand that's being pulled, and to prevent that brownout, you're saying, keep the power level even for everybody that needs it across that grid.
And that's its own interesting, complex challenge.
It sure is.
And the cooling, I'm hearing all sorts of startups in this space. So my claim that means this is going to happen soon. Liquid cooling is coming to stay for AI training.
Yeah.
I mean,
will they be novel liquids, or are we still talking about water?
It's actually a really interesting question. So it is clear that novel liquids have better thermal properties, but they have operationally, how do you want to balance the operational difficulty of what happens if this thing spills all over the place?
Yep.
And I remember I was in a data center where I wasn't there, fortunately, but I was managing part of a data center when a switch literally caught fire.
Mm-hmm.
And you don't really think about how the thermal properties of the stuff around the rack is going to react when there's a fire there. I mean, thank goodness somebody has, but I'm a software guy, right? That's not really my cup of tea. But what do you do when your server gets a leak in it? Is a pretty pressing question for this space.
Like a literal leak, not
a literal leak.
A memory leak or a packet leak. A literal leak,
a
leak of some novel liquid, some kind of a coolant that is toxic to the environment, presumably. And if it leaks, is it hazardous to humans? What happens if it's outdoors and it gets into the ground? And those kind of challenges.
And there are liquids that are hazardous to humans. I did see a demo where the sales guy actually drank some of the coolant. So there are kind of bio-happy versions of this, but I think they're bio-happy with a star is my, with kind of an asterisk.
He drank it, but he'd been building up a tolerance for a year and a half just for that demo. So
yeah, kind of like iocane powder or something, right?
It was the end of the quarter. He needed to book the sale. He's like, "Yeah, I'm drinking it, doing it."
So, but all of like everything that I've talked about is the cutting edge of somebody's research space right now, which is why I find it so interesting. Um, maybe we've gone a bit far afield from what might impact the day to day of what folks your listeners are listening to are looking for. But at the same time, I think the high level point is if there are companies that are looking seriously into getting into the AI training space, that like all of these things are things that are going to have to be tackled and considered.
My assumption is it's the hyperscalers who are interested in this sort of cutting edge research because they are presumably running up against the bounds of the power capability or the power generation they can expect.
Exactly. But there are a number of companies trying to compete with them, and it's actually interesting. So how do the hyperscalers potentially lose? And anything that says their massive infrastructure and massive existing deployment becomes a detriment because the game just changed. So if you think about like all of the traditional compute and network infrastructure that Facebook, Google, Microsoft, Amazon have deployed, and it's like, okay, all of that doesn't matter as much as the AI training side. Who can build that up better, faster? It's at an interesting shift in the curve right now for who might come out on top. So it's not just them.
For smaller companies that are maybe thinking about building their own AI or HPC clusters, they're not hyperscalers, Rob. They're not building gargantuan data centers. Do you have advice for them? Are there takeaways based on our conversation things you could recommend?
I guess what I would say is, there is expertise in high performance computing networks. And that's a place to start. It is back when I was a student at University of Maryland, I actually worked in an HPC lab. So like it's technology that exists. People know how to do it. There's not many people, and historically, it's not been all that interesting. So I would start by trying to look for folks with that background. There's a lot of problems right now that are non-obvious working into this space, like from dumb things like, can I even buy GPUs?
Yeah,
there's just a massive shortage of them going on right now. And by the way, like if you do Google search for like the most recent GPUs from NVIDIA, they're $30K a pop.
Wow.
You're like, well, I could buy a car or I could buy a GPU. So that's one. It's probably trite to say you've got a lot of homework to do, but I think in a way that I think I've never meant it in my professional career. There's a lot of homework for people who are going to try to get into this space. And it's hard to imagine that you're going to do better in the short term than the cloud providers. But the long term, who knows?
So given that, if I'm already going to try to tap some folks who've got experience with HPC, does that mean I may end up going InfiniBand anyway? Or if I'm trying to DIY it and, all my team has Ethernet experience, that's the better way to go in terms of building the networking infrastructure?
I guess what I would say is every company is going to have to make their own decision there. I think the accepted wisdom in HPC is InfiniBand. But if I were to build this myself, but I've built my own switch network operating system and know how to program chips at a low level and whatnot, I would definitely go with Ethernet. Right. So it's if you have somebody go on.
You go with Ethernet because it's your background, or because you think it's just better suited?
I think it is ultimately cheaper and can hit equivalent performance.
Okay.
But to Ethan's point, and I'll take the compliment, thank you, that most people probably wouldn't fall into that camp just yet. At the same time, I should probably call out, what is it? There's a high performance Ethernet group that just got started, Ultra Ethernet.
Yes, I'm going to ask you about that. What you thought that the effect of them were going to be?
I was very much involved in that in past lives, and I do think there's a lot of room for that to grow and end up with a pretty powerful option. But at the same time, it's currently not really commercial off the shelf. There's a lot of bells and knobs that need to be tuned. So.
I think that's the point of it, though. You're going to get to a commercial off-the-shelf solution once the Ultra Ethernet Consortium's done their thing.
Yeah. But is that going to be next year? Is that going to be in 5 years?
I'm hearing 2 years plus. Yeah. But okay. But you think they're going to have a positive impact on things? I mean, and again, the point I was making before is if I'm not Rob Sherwood and I'm trying to make a decision between Ethernet and InfiniBand, I'm looking at InfiniBand going, okay, it's costlier. And the other argument against InfiniBand is it seems to be harder to find expertise, people that actually know how to configure and administrate that system. And Ethernet, you have fewer barriers that way. And then, of course, as you said, it's cheaper.
But at the same time, if you look at traditional, what's great about HPC networks is, there's been, I'm not sure if you are familiar, if your viewers are, but there's a top 500 supercomputing, list
ranking. Yeah.
And you can go through and say, like, how's this one built? How's this one built? And they're almost all InfiniBand if they're not custom networking.
Fair enough. So I guess a subtext here then goes back to a point you made earlier. One of my research points doing my homework is maybe I don't want to build this myself because I'm gonna rent a GPU from the cloud more or less and do that. That's probably the right answer for a lot of folks.
I think the decision tree is, how critical is this to your business? How much are you going to do this? If the answer is not very or not that often, or I'm just trying to get started, the answer should be go to the cloud. And if the answer is I'm going to do this a lot, but we're not a cutting edge technology firm where like AI training is going to be key to our business, then I would buy a commercial off the shelf pre-integrated systems. And then, if you really are in the top 1% of this, then you start looking at custom solutions. But at the same time, that is the decision tree for, July of 2024. This is a wide open space and there's a lot of people doing a lot of interesting things here. And like, this could all change very quickly.
Let me ask you a provocative question, Rob, as kind of a closer. If I'm a startup or I'm a VC firm and I've got money burning a hole in my pocket, is there an infrastructure play in this that's there's a vacuum waiting to be filled and it would be money well spent to invest in a startup here?
So I really do think that things around power are really going to be where the bang for the buck is going to be. Like you said, it's limiting factor in getting things deployed. It's limiting factor in getting these things scaled out. Just the cost. I forget what it was, but it's something like every megawatt. I had this great snippet from a guy who ran one of the supercomputing centers. Every megawatt your DC consumes is like $10 million a year in OpEx. There's some easy ratio like that. And like, if you can get those numbers to change, that's where I would go after, so I think, optical circuit switches, that's one that I personally tried to chase. And I still think that there's value there.
Liquid cooling.
More on the liquid cooling, on the power technologies. How do we coordinate lots of inverters, across time? What they call, load shifting technology. So right now in the power network, there aren't very efficient, low cost buffers. So if you think of something like a battery, batteries are both expensive and, the amount of power you put in versus the amount of power you get out is not bad. But like, there aren't a lot relative to the amount of power going through the network. If you were to try to say create a buffer of 5% or 10%, it would be cost prohibitive. And so there's lots of people looking at advanced flywheel designs and, pumping water uphill in various forms and whatnot, trying to create what we in network would think of as like a buffer. And, I think there's a lot of interesting stuff there. I don't know, there's maybe as an ending point, I lived through mobile, I lived through the internet boom, if you want to call like Web3 with all the crypto stuff, another boom, lived through that. I have never seen a technology hype cycle as big as AI.
Yeah, it's saying something.
And I keep waiting for it to go the path of blockchain or crypto, and it hasn't, because AI seems to be we're seeing it be productized in a lot of different ways, mostly LLMs at this point, but other ways too. It does feel like there's something here, although I'm not yet convinced of the staying power. We'll see.
I'm convinced of the long-term staying power of something. I think that we will have this is the biggest bubble I've seen in my career, and one would think that would logically cause the biggest pop.
Mm-hmm.
And so I'm actually personally quite concerned about that. But I do believe that, fast forward 20 years from now, we will have, AI technologies in people's everyday lives in some way. Is it going to take over everything? I don't think so. But is it going to take over some things? Probably.
I mean, essentially what's happening is we're just building out a lot of compute, and somebody presumably somewhere will find a way to use it in some way that generates profit.
That's my favorite way of looking at this, which is, almost all the AI infrastructure is general purpose HPC infrastructure.
Mm-hmm.
And HPC has lots of applications, including, weather pattern prediction, including,
drug design.
And all sorts of things. And so even if the AI isn't as successful as people think it might be, and, there's all indications that it will be at least somewhat successful, like there's a whole bunch of knock-on effects that will happen as well.
Yeah.
Well, Rob Sherwood, where do people find you on the internet?
All over. Probably the easiest is I'm Capveg at Twitter, CAPVEG, and I refuse to call it X. I have a personal website, rob-sherwood.net, and I've got my company's website, netdebug.com.
netdebug.com to check out Rob's latest project. And thanks to you for listening to this week's Heavy Networking. You are an outstanding human, not just because you listened to this show all the way through, which is admittedly a bit eclectic, a bit out there, a bit eccentric even. You're not awesome just for listening to the show, but because of who you are. We appreciate you being part of the Packet Pushers community, and that community of ours keeps growing. You can be as much a part of it as you like, and it's all for free, no strings attached. And I got some options for you here. You could Number one, sign up for Human Infrastructure Newsletter. That's Drew and I. I'm Ethan Banks, and Drew Connery Murray is who I'm talking about. Drew and I research everything going on in the world of tech blogs, IT news, vendor announcements. We write it all up and we ship it every Thursday. We have another newsletter called Packet Capture. That's a summary of everything that the Packet Pushers team has produced this week. We don't sell your address to anybody. That would suck. Packetpushers.net/newsletters. Number two, you could join our free Slack community. Well over 3,000 people in that group, and more join every single day. We're adding new channels to the Slack group too. The most recent ones we've been adding: campus networking and firewalls. The firewalls one's been really popular, and routing. You can also talk to any of our show hosts there, including me and Drew, and please do. Packetpushers.net/community to join our Slack and tell your friends about it. And then finally, our community is growing with new podcast series. Here's the current lineup. We got a lot of shows for you here. Heavy Networking, Network Break, Packet Protector, that's our cybersecurity show, Tech Bytes, Heavy Strategy, IPv6 Buzz, Heavy Wireless, Network Automation Nerds, and then two brand new shows. Technically Leadership is aimed at those of you who are tech team leads, managers, or who aspire to be. And then Total Network Operations is for you folks who are operators and want to get a true structure and system in place and not just react to tickets all day. You really want to put that structure in place in your network operations practice. Again, thanks for all you do. And last but not least, remember that too much networking would never be enough.